Boeing Guidance Repair Center. I guess I've been here 2.5 years now, this site. So, but I guess the site has been there for 50 years. It was an Air Force base, Newark Air Force Base. And from day one, they were involved with developing guidance systems for Minuteman systems. And about 15 years ago, when the government decided they wanted to, just like all the time, cut costs, they went through a process called BRAC, which is reducing bases. So the community here decided it's a resource and jobs and an opportunity we want to hold on to. So they partnered with the government and said, can we put it out for private bid and have a company come in and run it instead of the Air Force. So that's how Boeing got involved in taking it over. So that was about 15 years ago that Boeing has done it. So we've been there for that long. Like I said, I've been there for 2.5 years. Working as I'm the chief engineer for the site. I run the engineering organization. I have 107 people working for me. Probably about 80 to 90 of them are engineers. The rest were different jobs. Now again, we repair the guidance repair systems, or the guidance systems for Minuteman III missiles. We used to do other systems there, but because of trying to have a more nuclear safe world, you know, the United States and Russia went through agreements and reduced the number of ICBMs. And so Peacekeeper, which was another system, is no longer active. We also repair guidance systems for some aircraft, B-1s, B-2s, B-52s, F-15, F-16s, and all the guidance systems. We do that work out there. So that's kind of what we do at that site. Like I said, I've been here for 2.5 years. I'm not a native Ohioan. Came from California. Was in California about 28 years. I'm originally from Pittsburgh, Pennsylvania, so I do know a little bit about the snow. That was one of the reasons why I went to California, because I didn't want to live in the snow, but here I am. Anyway, I was on the worked on the space shuttle program for about 18 years. Went over to ground missile defense for a while. Worked on, I don't know if you've heard of the project. It's called SBX. If you ever seen pictures of like an oil rig with a golf ball on top in the news, that's the project I was on. And then I came here to work on my CV. So that's a little bit about my background. But I'll take you through the Aerodynamics Challenge. We did this 2 years ago. And we learned through the process. I'm not a aerodynamic engineer by trade. Not my area of expertise, but we thought it would be good to do, and we decided to do the wind tunnel 2 years ago. Most of our effort was really dedicated to building the wind tunnel. We never did anything like that ourselves. Worked with some other engineers, and so that was our major accomplishment. We decided to go back and work on it again this year because, number one, we saw, just like everything, it could be improved, and we wanted to make it more user-friendly for the works so they can take over and use it. So that's what we're trying to work on now, is the computer interface and how it gets data from the wind tunnel. We didn't get as far along with the project as we thought we would. So that's what we're trying to improve for this year. But the wind tunnel still works. It still flows 2 wind speeds, 10 to 15 miles an hour. We were going for 3 at the time. The motor we got didn't work out. I did 2 speeds. But that's just like any project you learn as you go along. But if you were involved in that project, they just we're going to have the wind tunnel here. Because of the weather, they couldn't move it from storage. But if the teams wanted to go over and look at it, do their own specific measurements, they could have today. Flipped it on and proved once again that it still blows wind across the interface. So anyway, I'll take you through the little presentation. It talks a little bit about theory of flight, lift, and drag, because that's what was the reason we did this project. Again, Aerodynamics Challenge. Let's learn about aerodynamics, the basic equations in terms of lift, thrust, drag. We're part of this project, and what they have to do to demonstrate understanding of the concept. So you'll see a little bit of that material here. And whether you have to do it or not for your gliders are going to fly into the furthest or highest, longest, based on these equations and lift and drag, even though I can actually do the proper calculations, but all that contributes to how well your glider does. It's got to be light, it's got to fly long distances. So the concepts in your exercise, the same ones they're doing here when designing an airfield. It's no different. See if I can run this at the same time. Coincidentally, we had a briefing today. We talked about how to give briefings. We have these lunch and learns, how to give it a briefer. I'm probably breaking every rule in the book by doing this briefing the way I'm doing it. So I'm going back. Okay, so. Okay, so what's aerodynamics about? It's a study of forces and the motion of objects through air. It affects the motion of a large airplane, model rockets, gliders, or even the curveball that you throw during the summer. So it's the flow of objects through air. That's what the whole theory is about. So we're studying airflow so that they can make the shape of an airplane better, understand how the airplane works and how it affects airflow across that. Because how air flows across the foil, same way as how air is going to flow across your gliders, and they determine how well it glides. And so the basic forces on anything that comes through the air are lift and drag. So this foil that we would put in our wind tunnel and your glider still have to obey the same laws of physics. So when we first developed this, and it's part of the works philosophy, why we want to get people involved in aerodynamics. Okay, it's part of the greater STEM, science, technology, engineering, math, thrust that the works in the rest of the country is trying to do. So, came up with some reasons why we thought aerodynamics, one of the areas of study, is important. We all fly, we all travel, and we understand, fuel costs affect individuals and businesses and how much your ticket costs to fly your airplane. So you can go visit people over the holidays. And so the more efficient your airfoil is, the more efficient and lower your fuel costs are. And so we're trying to push engineers at every level to design projects and airfoils that are more efficient. The American Manufacturer Association recognizes this is important, and the only way you'll be more efficient is take a look at the designs, and the better the design will help us, again, decrease dependence on fossil fuels. And also we wanted to provide some kind of motivation to young engineers, people like ourselves, to say, hey, this is an area maybe I want to learn more about, get more involved with. So that's the whole point of why we're studying aerodynamics and the thrust of this aerodynamics challenge. What's the goal of this one? Design and construct efficient airplane wing airfoil using whatever materials you thought was more appropriate. We do make some suggestions, but we had a lot of these teams latitude to build their airfoil out of anything that they wanted. Hopefully you build the most efficient airfoil that maximizes lift and minimizes drag. We'll then take that foil and put it in our wind tunnel and test it out. And so part of the design exercise was to present their design process, test it, and then provide a briefing that shows the information that you use to calculate drag and lift that you calculated, and then we would compare it to your actual results and see how close your calculations came to the actual results. And so that was part of the exercise. So again, with determining how much airflow goes over the airfoil, we determine how little it has to lift force, and we want to minimize drag. So some who may or may not be real familiar with again, aerodynamics, pictorial shows the forces that act on any airplane. You have lift, drag, weight, and thrust. And that's what all the equations are based on. So, and then part of the exercise is, well, what part of an airplane contributes the most to those forces, and how can a design of an airfoil affect those forces. And so by aerodynamics, these are the things we want to take a look at theoretically in terms of what it means to design an airfoil. And we'll show some pictures. It's probably a little bit better to understand what we're talking about in terms of forward line and mean camber line when you see a picture. Pictures worth 1,000 words. So before we get into it, lift versus velocity. Basic as the velocity increases, so should the lift. That's what you're trying to prove. That's what this equation is showing you here. The faster you go, the more lift you should have. As the air flows across the airfoil, you should give you lift as the air flows. And so part of the picture on the left is showing that depending on your design of the airfoil, we'll show you some examples that some of the teams could use. Determines how fast the air flows over that structure. Another thing, different airfoil shapes provide different amounts of lift. So there's the Wright-Brother airplane that had their airfoil in rudimentary design. Other birds of flight have their wings or airfoils. Ostrich definitely has an airfoil, but it's not very flyable structure. The picture on the upper right is probably, say for Boeing, the ultimate design right now is a 787 airplane with this airfoil. And I don't know if you've ever seen pictures, that airfoil flexes in front. And it will go up almost 90 degrees. They've done it in tests just to see if it would break, and they haven't broken it. But again, that's the ultimate. That's made out of composites. Something like this, but very flexible structure. Again, the whole point is very different airfoil shapes and designs can either create lifts or maximize your drag, and that's what this exercise, again, we'll figure out which shapes work the best. Again, here's some...
is that plane the one with the composite fuselage too?
Yes. Yeah, I don't know what the percentage of it's composite. Yeah, part of the fuselage is composite. The wings are almost entirely composite. Just decrease weight. But again, here's some of the theory we talked about. If you were going to design some of the terms that we line, this is the chord, basically it's different kinds of shapes, airfoil shapes that have been developed in the past. Some of them have more advantages over others in terms of the amount of lift, drag, and gliding time in the air. Glider, you want to be able to glide a lot longer. Passenger airplanes want those kinds of characteristics within their airfoil. They want to be able to glide long distances with less energy. Fighter aircraft, although, for example, they want to be able to turn quickly maneuver, so their airfoils are going to be a little different shape than a plane that just wants to fly long distances, basically straight level. And so depending on what you want your aircraft to do, another reason why the design might change. So you can see you can put different designs within our wind tunnel airflow, and you'll get different airflow over, and will cause different characteristics of different drag. That's why I would say, automatically know that a block of wood would be the worst airflow that you would want, depending on what your application is. So that's why we tried when we first designed, it's not the limit to the teams and what their airflow will look like. Just want to have some additional creativity, because when you say airflow, a certain picture comes to mind. The upper, at the top might be the one that you're thinking of. There could be some kind of creative design. Someone would come up and have a better lift than standard traditional airflow. So we wanted to encourage that kind of creativity. So for our exercise, this is a cutaway of part of the wind tunnel. This shows the air flowing through this area. And this is the volume of space that we gave the various teams that could fit their airfoil in. And so within that volume of airspace, they can design and use it any way they want. So gave them 4 inches of width, with 12 inches of height and 22 inches of length. They could use any geometry to fit within that volume. They could use anything they wanted in terms of materials: wood, plastic, metal, wire mesh, lacquer, epoxy, to design their airfoil. So that's some of the specifications for this project. The other thing that was kind of important to us, we spent a lot of time, is, well, how are we going to mount their airfoil in the wind tunnel so that we can test it, and so that we can try to make it as universal engineered as possible and as easy as possible to mount. So the airfoil must incorporate, be able to mount on a slot that's within the tunnel. And this is one of the airfoils that was used, and as you can see, they designed their airfoil has this little plastic slot structure, so all it did was just slid right over. So that's how they designed their structure to fit on that bracket, and so then out the wing can move around. So some of the variables to consider: your sweep angle, twist, groove tip, airfoil shape, material thicknesses, and so all of those went into the design of this airfoil: how thick it was going to be, how far this length is, how much they were going to sweep it. And so this is the design that they came up with.
And that is the 2011 winning wing.
Did a good job. Another question is why we're doing this, why we're testing the wind tunnel.